Hello, we will continue with lesson 3 of sectoral structures theory. We're gonna try to get through the geometry and trigonometry parts as fast as we can so we can focus more on the algebra. So today we're gonna introduce the concept of a beta joint. Last lesson we saw alpha joints where we have two continuous sectors joined by an alpha joint. Today we're gonna find the other main way that we will connect sectors to create sectoral structures, and that is through beta joints. So basically, if we have two congruent sectors, circular sectors, such that the edge of the first one is continuous with the edge of another one, starting with this vertex here and ending with the vertex of the other sector. Additionally, the arc of the first sector and the arc of the second sector are also continuous and attached at this point, which we will call a beta joint. So another way to think of this is if you have two tangent circles, here's the center of the first one, here's the center of the second one. We draw a line between the two centers, and then we create a sector here, and we create a congruent sector here, and this point of tangency becomes the beta joint. And this will explain a lot of the relationships we will see in future lessons. Now, for continuous sectors, we use the wedge. So we said V is continuous with U using a wedge symbol. For alternating sectors, we will use this upper wedge or up wedge and down wedge like that. And we will read it. V is alternating with U instead of continuous. So we will say up, down like that, and we will read it as V is alternating with U. For example, if we have sectors A, B, C, D, we will write it as A is alternating with B, is alternating with C, is alternating with D. Now, we don't call this a part, but rather each of these is its own part. So a part is made of only continuous circular sectors. Now I'm going to get a little bit deep into the geometry and trigonometry, but I promise this is not the essence of sectoral structures theory, but we have to get through this initial part. The first concept we need to see is that if we have two alternating sectors, an important property is that the furthest two edges, so this edge L of this sector and edge M of the other sector, are parallel. And this is pretty easy to prove. We have these interior angles. We know this is theta and this is theta, and they are congruent, so therefore these two must be parallel. Now let's look at a little bit some of the more complicated concepts. Now if we have these two alternating sectors, we can define the midpoint of each of these arcs, M and M here. That's pretty easy. Now I can draw a line from the vertex to the midpoint, and we know the length of this is going to be 1 because we said the radius is 1. And I can do the same with this one here. Now let's do something else. Before we go on, notice that these two are also parallel to each other, these two midpoints, or these two radii. Now let's continue. We're gonna draw a tangent to this midpoint here, that we're gonna change the names. Instead of M, we're gonna call this midpoint X and this midpoint Y. Now let's draw a tangent to Y, tangent to the circle. We know it has to be perpendicular to this radius, and we have a right angle here. Now we know these two are parallel, so this must also be a right angle. Then let's draw a tangent to the circle at X. We're gonna have this other line, and this must be perpendicular and this must be perpendicular. So what do you notice? We end up with a rectangle in the middle of the alternating sectors. We're going to refer to this as the central rectangle. Let's do a little bit of geometry and trigonometry related to this rectangle. We're going to isolate it here. Let's begin with some of the angles of this rectangle. To begin with, we know that we have these two are right angles, and of course these other two, but we want to see the angles that are free. So these two are right angles. What else do we know? If we look at if we look at this angle right here, sorry, I'm gonna pause a little bit. If we look at this angle right here, that is formed by the intersection of the line segment connecting X and Y, so the segment connecting X and Y, and formed also by the line segment that is connecting the two vertices. So let's try to draw it in green so it's a little bit more apparent. You see it right here. Then we're going to refer to this angle here as sigma. Let's begin by calculating sigma. This will help us unlock the rest of the angles. We know that this is a radius of length 1, this is a radius of length 1. So therefore this is sigma, and this must also be sigma. Notice we also already know this angle. It is half of theta, which is theta over 2. Therefore, we have figured out what sigma is. Sigma is half of pi minus theta over 2. And remember, we're doing this in radians. So we have unlocked sigma. So here we have sigma, and we also have sigma over here. Now, what else can we tell about this, about these angles? We know that the angle here, if you notice right here, we said is also sigma. So if we continue if we impose this on the rectangle, then we know that this one is also sigma, because if we continue this, we get our triangle again. So this one is sigma, this one is sigma. The same here. If we continue like this, we know this one is sigma and that one is sigma. We figured out the sigmas here. This leaves us with this angle right here, which is delta. And we already know the other three, so this is easy. Delta is equal to 2 pi minus the right angle, pi over 2, minus the 2 sigmas. And by substituting, we can end up, and you can check this on your own, delta ends up being 1/2 of pi plus theta. So notice we're trying to make all the angles in terms of theta. This is theta here. And that way we connect them all to one of the core properties of the sectors. So we're expressing them all in terms of the sectors. So we have delta. We figured out our deltas. What else do we have? Or what else is missing? We have these two angles. We're going to call them tau. And this is also pretty easy. Tau is simply pi minus sigma, which ends up being pi over 2 plus theta over 4, or 1/2 of pi plus theta over 2. We also have phi right here. Again, this is pretty easy. This is simply pi minus delta, and it ends up being pi over 2 minus theta over 2. Notice everything can be expressed in terms of the original theta. Finally, we have this angle rho over here, and we already know these two angles of the triangle, so rho is simply going to be equal to theta over 4, and you can double check on your own. So a lot of really interesting properties. Every angle within this central rectangle we were able to express using only theta, which is the central angle of the sector. Let's look at now some of the length. Let's begin. Let's go back to this original triangle we started with. We know this is these are radii, each of them is equal to 1. We're going to call this line segment connecting the beta joint and the midpoint y in this case. So beta to y. We're going to call this side m, and we're going to use the law of sines. We'll figure out that m is equal to sine of theta over 2 over sine of sigma. We're going to simplify this. Please double check. We're going to get m is equal to sine theta over 2 times tangent of theta over 4. And again, we simplified using trigonometric rules. Now, if we extend this m all the way here, we get 2m. We're going to call this xy, or we're going to call it d. So the length of xy, which is this diagonal of the triangle, that's why we're going to use d, of the rectangle. We'll say xy equals d equals 2m. So notice now we have this other right triangle, which has d, the width of the rectangle, and the length of the rectangle, and it's a right triangle, making things much easier. The length of this, of the rectangle or of the triangle, is going to be d cos sigma. We're going to simplify this to L equals, and remember this is simply 2 times m. 2 sine theta over 2 tan theta over 4. And then we're going to get w right here. It's going to be w equals d sine sigma, which will simplify to 2 sine theta over 2. Pretty simple. So this will be the width. Now the area of the central rectangle, we will write it here. It will be 4 sine squared theta over 2 tan of theta over 4. So this is very interesting. For two alternating sectors, we have a way to find the area of the central rectangle simply by plugging in the value of the angle. And it will generate a nice looking graph with a maximum area reached when theta is equal to 4 pi over 3. So take home the concept of alternating sectors, the concept of a beta joint, the way we express alternating sectors, and the idea of the central rectangle. Thank you.